People working on transmission and distribution systems are responsible for their own safety and the safety of others. And to work safely, you need to know some of the safety hazards you must watch out for. We're going to take a look at 3 electrical hazards: arcs, faults, and the invisibility of electricity. Then we'll briefly look at some of the general safety practices that can reduce the dangers that these hazards present. Now, a safety hazard is a condition or an action that places your health at risk. For example, a condition such as the invisibility of electricity can be a safety hazard. Right now, current is flowing through these lines, yet there's no visible indication that the lines are energized. The invisibility of electricity is a hazard because it makes it possible for a worker to mistake an energized line for a de-energized line. An action, such as not wearing required protective equipment, can also be a safety hazard. If a man working on these lines does not wear the protective equipment required for working on a live or energized circuit, he could be shocked or even killed. However, by being aware of the hazards and following company safety procedures, such as wearing the proper protective equipment, he can work safely on these lines. Now, in addition to the invisibility of electricity, arcs and electrical faults are 2 other electrical conditions that can be safety hazards. Let's first look at arcs. An arc is a bright discharge of electricity that crosses a gap in a circuit. Arcs often occur when a switch on an energized circuit is opened. In this simplified illustration, this line represents part of an energized circuit, and this represents a switch with 2 contact points. The arrow shows the direction in which current flows. When the switch is opened, there is a gap between these 2 contact points. An arc can be a temporary discharge or electrical flash from one contact to the other, or it may be a sustained electrical discharge. Now, both kinds of arcs are safety hazards because they can generate heat and cause fires. An electrical fault is a defective point in a circuit that can interrupt the normal flow of electricity. Now, faults can be caused by grounding, short-circuiting, breaking an energized circuit, or the failure of insulation. Let's use an illustration to show the safety hazards represented by 2 kinds of faults: ground faults and short circuits. Now, here we have energized overhead lines, insulators which support the lines on the pole's crossarm, and a neutral line connected to a ground. A ground is an intended path for current to flow to the earth. During normal operation, current flows through the lines. A ground fault occurs when a low-resistance electrical path to ground is created unintentionally by a defect in the circuit. For example, a broken insulator is a defect which can create an unintentional path to ground. Current which normally flows through the line can seek an alternate flow path across a material with low resistance, such as this broken insulator. Under the right conditions, current can travel through this line, across the insulator and the crossarm, and through the closest ground. Now, this type of fault can be extremely dangerous if a worker happens to be near the location where the fault occurs. The worker could suffer burns resulting from arcs. Now, short circuits can also be extremely dangerous. A short circuit is a fault caused when uninsulated energized wires cross one another and create an unwanted electrical path. Now, this can occur when a car accident causes damage to the lines. When the wires cross, like they do here, current jumps to extremely high amperage levels, levels that can exceed the capacity of system equipment. High levels of current can generate extreme heat and cause arcing. None of the electrical hazards you just saw can be eliminated from electrical systems. However, you can reduce the dangers associated with these hazards by following safety practices. Now, safety practices are rules and guidelines established by your company to protect you from electrical hazards. Some of the general safety practices involved in performing most jobs include planning a job, inspecting a job site, wearing required protective equipment, and following the specific safety procedures that your company requires for performing a particular job. Planning a job involves determining the procedures and safety requirements necessary for completing the work. If you're working as part of a crew, it's important to discuss the job beforehand. Each member of the crew must know the proper safety procedures required for performing his part of the job, and he must use them to protect himself and others from electrical hazards. Now, inspecting a job site includes verifying that you're at the correct location. Checking with a map can help you make sure you're in the right place. You should visually inspect each site to make sure the equipment there matches the equipment you're assigned to work on. You should also note equipment damage or anything out of the ordinary that could indicate the presence of unexpected electrical hazards. Protecting yourself involves inspecting the tools and equipment you'll be working with to make sure they're in good operating condition. You should also wear the personal protective equipment that the job requires. Then you can perform the job according to the safe working procedure established by your company for the specific job you're working on. Okay, we've talked about some of the electrical hazards that make it possible for accidents to happen, and we've looked at some of the general safety practices that apply to most jobs. Now, as we go along, we'll see how protective devices can help ensure personal safety. And we'll see how electrical circuits can be de-energized and made safe for certain electrical repair jobs. Protective devices help safeguard employee lives and system equipment. That's why you'll find protective devices located throughout the electrical systems you'll be working on. Now, what we'll do now is go over some of the general characteristics of protective devices. Then we'll look at fuses, circuit breakers, and reclosers, and see how these devices protect personnel and system equipment from damage due to faults. Now, in terms of electrical safety, a protective device is any mechanism that helps prevent electrical hazards from injuring people or damaging equipment. Some protective devices, like this tester, help protect people by detecting electrical hazards. A tester can give a visual indication of the invisible presence of electricity in a line. Now, this can help workers determine the safety requirements for a particular job. Other protective devices, like this fuse, are built into electrical systems, not only to detect hazards, but also to operate automatically to protect system equipment. A fuse can operate automatically to de-energize a circuit if it detects a fault in a line. You'll be seeing many types of protective devices throughout this program, but for now, we'll concentrate on 3 devices that are built into electrical systems to protect against faults. We'll look at fuses, circuit breakers, and reclosers. Now, basically, a fuse consists of a wire or metal link enclosed in an insulated housing. The fuse link melts, opening a circuit when levels of current exceed the safe capacity of the circuit. We'll use a simplified illustration to show how it works. Here's the fuse housing, and here's the metal link. Now, fuses are generally located along the normal power path in a circuit. Current flows through the fuse this way. If a fault develops in the circuit, current increases, creating heat. When the current exceeds a safe level, the metal link inside the fuse housing melts. This opens the circuit and stops the flow of electricity, de-energizing the circuit. De-energizing the circuit prevents the high current levels from damaging system equipment. A circuit breaker is an enclosed electrical switch. Like a fuse, it's used to help protect circuits from the effects of faults. Now, this simplified illustration shows the inside of a circuit breaker. These are the switch contacts. When the switch contacts are in the closed position, current flows through the breaker and on to the rest of the circuit. If a fault occurs, current rapidly increases. And when the circuit breaker detects the fault, the switch contacts automatically open. This de-energizes the circuit and prevents equipment damage. A recloser is another electrical switch that can detect a fault in a circuit. A recloser works in a manner similar to a circuit breaker, except that it can reclose its switch contacts after a preset time period. This is a simplified illustration of the inside of a recloser. It contains two switch contacts. When the switch contacts are closed, current flows through the recloser. If a fault is detected in the circuit, the switch contacts automatically open. This de-energizes the circuit. After a preset time interval, the contacts close. If the fault is still detected, the contacts will open again. The contacts will attempt to reclose for a preset number of times. If the fault clears itself from the circuit, the contacts will remain closed and the circuit is restored to normal. If the fault does not clear, the recloser will lock open after a certain number of attempts have been made to close the circuit. The circuit remains de-energized until personnel correct the problem. And now that you've seen how fuses, circuit breakers, and reclosers work individually, let's see how these protective devices can be arranged in an electrical circuit to protect against faults. We'll use a simplified illustration of an electrical circuit to show how these components operate. Symbols on this diagram represent a power source, a circuit breaker, a fuse, a recloser, and a three-phase overhead line. The line consists of a feeder line and two branch lines. During normal operation, current flows from the power source through the circuit breaker and through the main feeder line. Current also flows from the feeder line through the recloser to this branch line. And it flows through the fuse to this branch. So current normally flows through the main feeder line to the lines branching off it. Now, like most electrical hazards, faults can occur almost anywhere in an electrical system. Suppose a fault develops here. The current in the line increases rapidly. When the current gets high enough, the fuse opens to break the circuit. This de-energizes the branch line, but protects the rest of the electrical system from the fault. Therefore, in addition to protecting system equipment, the fuse helps the system continue delivering power to the remainder of its customers. Now, suppose the fault occurred here instead. As the current in the circuit increases, the recloser detects the change and switches open, de-energizing the line. Now, this protects the rest of the system from the fault and allows power delivery to continue. At certain timed intervals, the recloser will attempt to close the line. If the fault has not cleared itself, the line will again be de-energized. However, if the fault does clear, the recloser closes its contacts again and the line returns to normal. Now, if the fault occurred here on the feeder line instead of the branch lines, the circuit breaker must protect the entire electrical circuit. When it detects a fault in the line, the circuit breaker switches open. This de-energizes not only the feeder line, but the branch lines as well. That's because the circuit breaker in this circuit is located between the power source and the rest of the electrical circuit. Now, in this case, the feeder line and both branch lines are protected from the fault. When the fault is cleared and the circuit breaker is closed, power delivery will resume. Well, that covers some of the basics of protective devices. Now, we've presented the basic design and function of these devices for easier understanding. In many electrical systems, these devices are much more complex, both in their construction and operation. So you should take a closer look at how the specific devices work in your system. And we'll be discussing protective devices in greater detail when we begin looking at the role that switching plays in the job of de-energizing circuits for maintenance and repair work. Live conductor wires and electrical components can kill or injure workers when safety procedures aren't followed. Oftentimes, these wires and components must be de-energized so that maintenance or repair work can be performed. If you're assigned the job of de-energizing a circuit and making it safe to work on, you'll need to know the safety procedures of switching, tagging, testing for dead, and protective grounding. This time, we'll focus on the procedures of switching and tagging. We'll see how switching is used to de-energize a circuit and how tagging can help prevent a circuit from becoming energized accidentally. Now, switching is performed by using protective devices to energize, de-energize, or isolate circuits. You should already be familiar with two of the most common switching devices, circuit breakers and disconnect switches. Circuit breakers can be used to energize or de-energize electrical circuits. To energize a circuit, switch contacts inside the breaker are closed. This allows voltage to pass through the breaker and energize the outgoing circuit. To de-energize a circuit, the switch contacts are opened, breaking the circuit and removing power from the line. Disconnect switches are used primarily to isolate a circuit from its power supply once the circuit has been de-energized. Isolating is a secondary protective measure. It creates a visible break in a circuit so that if the circuit breaker is closed accidentally, the circuit remains de-energized. Breaking a circuit under load can be dangerous, particularly if the circuit is carrying high voltage. That's because there's an increased chance of arcing when high voltage circuits are opened. Arcs can cause fires, injure personnel, and burn up equipment. And to keep you safe from the danger of arcs, circuit breakers are designed with special protective features. For example, arcs usually occur at the switch contacts where the circuit is broken. Now, that's why circuit breakers have contacts enclosed in a protective housing. This helps keep arcs contained and away from personnel and other equipment. Circuit breakers are also designed to extinguish the arcs caused by opening a circuit under load. In fact, circuit breakers are usually classified according to the method they use to extinguish arcs. Some circuit breakers use air to extinguish arcs, some use gas, and some use oil. Let's see how each of these breakers works. Air circuit breakers use a blast of compressed air to extinguish arcs. This simplified illustration represents the inside of an air circuit breaker. Its components include two switch contacts, an air blower, and a protective housing. Now, the air blower and switch contacts are timed to work together. When the switch contacts are opened under load, the blower releases a blast of air at the space between the contacts. This extinguishes the arc. Whenever the breaker is opened, this same process occurs. Gas circuit breakers use a blast of non-flammable, non-conductive compressed gas to snuff out arcs. This simplified illustration represents the inside of a gas circuit breaker. The parts of a gas circuit breaker include two switch contacts, a gas blower, and a protective housing. The gas blower and switch contacts are timed so that the blower releases a blast of gas when the contacts are opened, and the arc is extinguished. Now, oil circuit breakers use oil to put out arcs. This is a simplified illustration of an oil circuit breaker. Its parts include two switch contacts and a protective casing. The casing is filled with oil so that the switch contacts are submerged. When the switch contacts are opened, oil floods the gap between the contacts and extinguishes the arc. Now, this process is repeated whenever the breaker is opened under load. When you're using switching devices to de-energize a circuit, it's absolutely critical that you know which devices can be operated under load and which ones can't. Most circuit breakers are designed to be opened under load because de-energizing circuits is one of the basic functions of a breaker. With disconnect switches, this is not always the case. Some disconnect switches are designed to be opened under load, but many others cannot be opened until the circuit has been de-energized. You need to have a clear understanding of the differences between the two types of disconnect switches so that you don't make the mistake of opening the wrong switch under load. This could cause sustained arcing and you could be seriously injured. Fortunately, disconnect switches have certain features that let you know whether or not they can be operated under load. We'll look at examples of these two types of switches, and I'll show you what I mean. This is one kind of no-load disconnect switch. It's called a no-load switch because the circuit must be de-energized before this switch is opened. Its parts include a disconnect assembly, a switching arm, and switching contacts here and here on the switching arm. Note that the switching arm is made of one solid piece of metal. In this case, it's a knife blade. When a circuit has been de-energized, the circuit can be isolated by separating the switch contacts. This creates a visible break in the circuit. There is no arc to extinguish because the circuit was previously de-energized. Remember that no-load switches must be operated in sequence. In other words, they should be opened only after a circuit breaker is operated to de-energize the circuit, and closed before the circuit breaker is operated to energize the circuit. A load break disconnect switch can operate under load to de-energize and isolate a circuit. Like the other type of switch, its parts include a disconnect assembly, a switching arm, switching contacts here and here, and a latch. Note that the switching arm in this case is not one solid piece. It contains a cylindrical housing or fuse tube. And inside the fuse tube is a fuse link. At the hinge in the switching arm, the fuse link is connected to a latch. To de-energize and isolate a circuit under load, a hot stick can be used to push up on the latch. Pushing up on the latch breaks the fuse and causes the switching arm to spring open. Because the circuit is broken by the fuse, any arc is contained and extinguished within the fuse tube. Other load break switches can have arc breaking devices attached to them. These devices can help distinguish a load break switch from a no-load switch. Whenever you open a switching device, whether it be a disconnect switch or a circuit breaker, you should place a tag on the device. Tagging protects workers by letting others know the status of a circuit. For example, if you opened a breaker to de-energize a circuit for repair work, the circuit must remain de-energized until the work is completed. A tag lets others know who's working on the circuit and why. Most important, the tag also serves as a warning that the breaker must not be closed. Closing the breaker would, of course, energize the circuit and endanger anyone working on the circuit. Switching and tagging are two of the safety procedures involved in de-energizing a circuit and making it safe to work on. We saw how circuit breakers and disconnect switches are designed to protect personnel and equipment from the hazard of arcing. And we covered some of the differences between load break and no-load disconnect switches. When you come back, we'll see how another electrical hazard, the invisibility of electricity, can be overcome by using protective devices and following safety procedures. Are these lines live or dead? You must ask yourself this question every time you determine the safety requirements for a particular job. Now, since you can't see electricity, the only way you can tell for sure whether or not the wires are dead or de-energized is to test them. As we take a look at testing, we'll show you 3 kinds of testers, and we'll demonstrate how they can be used to check circuits for dead. Now, a tester is a detector or metering device that detects the presence of voltage in a circuit and therefore can determine whether or not a circuit is dead. It's very important to test for dead before assuming a circuit is de-energized and safe to work on. Now, suppose you have several jobs to perform on a circuit and the lines were de-energized before you started. A circuit breaker and disconnect switch were operated to de-energize and isolate a circuit. And you tagged these devices out according to company safety procedures. Now, since you've taken these steps, you could safely assume that the circuit is dead, right? Wrong. Accidents, equipment malfunctions, and certain electrical conditions could cause the circuit to be energized when it comes time to perform your work. That's why you should always assume that a circuit is live until you've tested it. Let the testing prove whether or not a circuit is dead. Now, we'll look at 3 types of testers: noisy testers, statoscopes, and phasing test sets, and see how they're used to test a circuit for dead. But first, let's discuss some considerations that apply to testers in general. Every tester has a safe operating range, requires routine inspections, and must be used properly to get accurate test results. For example, this phasing test set has a safe operating range from 0 to 16,000 volts. If you used this tester on an energized circuit that exceeded this range, you could damage the tester, or worse, get a false indication of the absence of voltage on a circuit. Now, in this situation, assuming the circuit is dead could place you in danger when you work on the circuit. So before you use a tester, make sure the circuit you're testing is within the correct operating range of the device. Now, you also need to inspect a tester both before and after you use it to make sure it's in good working condition. If a tester is damaged, it could give you an inaccurate reading. And to test a circuit properly, you should use a tester on all the lines at the immediate work site. Discovering one line in a circuit is dead is no indication of the status of other lines. Under certain conditions, one line may be dead while other lines on the same circuit may be live. So it's important to test each line to confirm that the circuit is de-energized. Now, the first tester we'll look at in detail is a noisy tester. A noisy tester uses sound to indicate the presence of voltage. This tester consists of a molded case with a slotted tube and a test button, which is located on the bottom of the case. Before using the tester, you should inspect it to make sure it works properly. This particular tester is battery operated. You check the battery by pressing the test button. If the tester sounds, the battery is in good condition and the tester can be used. To make sure the tester will detect voltage, you secure a hot stick in the slotted tube and extend the tester to an energized source. The hot stick keeps you a safe distance from the energized lines. Again, the sound indicates the tester works on a live source. Now you can test the lines at your job site. This 13 kV circuit is within the operating range of the tester. The tester is extended up to each line until it touches. If there is no sound, the results indicate that the lines are dead. After testing for dead, check the tester a second time to confirm the results of your circuit test. A statoscope is another type of tester. It uses a glowing light to indicate the presence of voltage. This tester consists of an insulated pole with a hand shield and a gas-filled tube, which is located inside the pole. The tube glows when the statoscope detects voltage in a circuit. You can check the statoscope to be sure it's working by holding it next to an energized spark plug, or extending it up to a known energized line. In either case, the voltage present should cause the tester to glow. Once you've checked the tester, it's held up to each line in the circuit. This tester should touch the line. The circuit being tested here is within the operating range of the tester. Now, since the tester doesn't glow, the test results indicate that the lines are dead. The statoscope is then rechecked on a live power source to confirm that the test results are accurate. So far, the testers we've looked at only give an indication of whether or not voltage is present on the lines. However, there are times when you may need more information, like how much voltage is present. The third type of tester we'll look at can give us this information. It's called a phasing test set. This phasing test set uses a meter to indicate voltage is present in a circuit. It works within a given range. The parts of this tester include two insulated poles with probes or hooks. A voltmeter is attached to one pole, and a reel of cable is attached to the other. The cable extends between the reel and the voltmeter. To inspect or check this type of tester, first, one hook is placed securely on an established ground. Then, to create a complete electrical path from the phase line to ground, the other hook is placed on an energized line. Now, whenever using this tester, be sure to keep the cable in the clear. If the tester works properly, the meter measures phase to ground voltage. Now the circuit can be tested for dead. With one hook on an established ground, the other is placed on the phase line you're testing. A zero reading for this line indicates there is no measurable voltage present. The phase to ground test is repeated for the other two lines on the circuit. It's important to test all the lines on the de-energized circuit you'll be working on. After the circuit has been tested, recheck the tester to be sure that it works and your results are accurate. Another way to test the circuit with a phasing test set is to place the hooks on two phase lines. This method is used to check for the presence of phase-to-phase voltage. This voltage reading indicates the circuit is live. As with the other testers, the phasing test set should be checked on a live source after it's used. You've seen how noisy testers, statoscopes, and phasing test sets confirm whether or not a circuit is de-energized. We also looked at some of the steps you need to take to ensure your tester gives you accurate results. In the examples we showed you, the circuits we tested proved to be dead. However, that won't always be the case when you're testing out in the field. If a line was supposed to be dead and voltage was detected by a noisy tester, a statoscope, or a phasing test set, it could mean that there are electrical problems in the system, or that a circuit has another power supply. In either case, the circuit must be cleared before you proceed to work on any lines or components. Remember, you should always assume that a circuit is live until you've tested it and confirmed that it's dead. Now, once you've confirmed a circuit is dead, you can move on to the next procedure, which is protective grounding. Grounds are necessary to protect the worker just in case the de-energized line becomes energized. We'll explain protective grounding in more detail when we return. So far, we've gone over some of the safety practices that enable you to perform jobs on de-energized circuits. Switching can de-energize and isolate a circuit. Tagging alerts others to the status of the circuit or equipment being worked on. And testing confirms whether or not the lines in a circuit are dead. Protective grounding is another safety practice that helps make de-energized circuits safe to work on. Protective grounding is creating an electrical path to ground by installing one or more electrical conductors between the de-energized circuit and the ground. This path can protect you by maintaining the circuit at or near ground potential should the circuit suddenly become energized. Now we'll look at some of the conditions that can cause de-energized lines to become energized unexpectedly, and discuss two types of grounds. We'll also go over one method of installing a protective ground. Let's start by seeing how a de-energized circuit can become energized accidentally. To de-energize this circuit, a switch was opened and tagged out. If the switch is tagged incorrectly or not tagged at all, it could be closed by personnel not aware of work being done on the circuit. This could cause the lines to suddenly become energized if the circuit hasn't been isolated and grounded. Here we have one set of energized lines and one set of de-energized lines. A storm or an accident can cause one of these energized lines to break and fall across the de-energized lines. This can cause the de-energized circuit to become energized accidentally. In addition to accidents, certain electrical conditions, such as static electricity, may also cause a circuit to become energized. For example, a strong wind can create friction on de-energized lines. The friction, in turn, creates static electricity that can build up and energize the lines. There are two other conditions that can create electrical charges in previously de-energized lines. These situations involve electric field coupling and magnetic field coupling. Electric field coupling is the transfer of electricity from an energized conductor to a de-energized conductor through a medium such as air. This can occur when a line carrying a high level of energy is located in close proximity to a de-energized line. The air between these lines can pass a certain amount of electrical charge from this line to this line, energizing the line. Magnetic field coupling can also transfer electrical charges. Magnetic field coupling is the transfer of electrical charges from an energized line to a de-energized line through a magnetic field. Now, this can occur when the magnetic field surrounding a live line crosses a de-energized line. This can induce voltage in the de-energized line and cause the line to become energized. We've seen several ways in which de-energized lines can become energized. Now, if you're working the lines as if they're energized right from the start, you'll be wearing protective equipment and following safety procedures that can keep you safe from these hazards. However, if you're working the lines de-energized, the best way to protect yourself is to ground the circuit. Ground switches and temporary grounds are two devices that you can use to ground a de-energized circuit. They're often used in conjunction with established grounds. An established ground is an electrical path to ground that's built into an electrical system to protect that system from the effects of faults. Now, this type of ground prevents the high current caused by faults from endangering personnel and from damaging components and equipment. A ground switch is a device connected to an established ground that allows you to open or close the electrical path from a circuit to ground. When a circuit is energized, the ground switch is normally in an open position. Once a circuit has been de-energized, tagged out, and tested to be sure it's dead, ground switches can be closed to protect personnel and system components while maintenance or repairs are performed on the de-energized circuit. Closing the ground switch completes the electrical path between the circuit and ground. A temporary ground is an electrical path between the work area and ground that's installed on a de-energized circuit for a short period of time. Temporary grounds are often used when maintenance or repair work is performed on a de-energized circuit. This type of ground will protect workers by keeping the work area at or near ground potential. Then, if the de-energized circuit should suddenly become energized, current flow is directed away from the work area to ground. Generally, temporary grounds should be located as close as possible to a work area without obstructing the job. They should also be located between the work area and all possible power sources. A grounding set is one type of temporary ground. This one consists of 3 grounding jumpers. Each jumper is a length of insulated cable with a ground clamp attached to each end. The jumpers are clamped between an established ground and the de-energized circuit wires. You can use a ground switch to ground the circuit when you're working near substation or switchyard equipment, and for added grounding protection when you're out in the field. You install grounding sets when you need grounding protection at your work site. We'll show you one way that a de-energized circuit can be grounded, but keep in mind that your company's procedures may be different. To install a temporary ground, you must first test the circuit to make sure it's de-energized. Grounding an energized circuit is a serious hazard. These grounds are designed to be applied only when a circuit has been de-energized. In this example, one end of the jumper cable is attached to an established ground. The other end of the jumper is attached to the center conductor wire. Each of the other conductor wires is attached by jumpers to the center conductor wire. This creates one electrical path to ground for all 3 of the conductor wires. Now the worker can complete the maintenance on the lines safely. There are some other things you need to consider when grounding a circuit. You want to be sure that your grounds are approved by your company. If work will be performed at several locations on a circuit and grounds are installed far from the work location, additional grounds may need to be installed close to the work area. Proper precautions must also be taken while installing grounds. You must follow your company's specific grounding procedures and use the protective equipment required by your company. Now that covers the basics of protective grounding. We've discussed ground switches and temporary grounds and explained how various circumstances can cause de-energized circuits to become energized. Before you start working on any de-energized circuit, see that you're grounded. Just because it's de-energized when you start a job is no guarantee that it won't become energized later. When we come back, we'll see how the safety practices of switching, tagging, testing for dead, and protective grounding are applied to a specific job in the field. By now, you're familiar with some of the basic safety procedures involved in preparing to work on a de-energized circuit. You've seen how to switch and tag out a circuit, test for dead, and ground a circuit once it's been de-energized. But these individual procedures make more sense when you see how they all fit together. So let's look at a job and see how all these procedures can be applied to help ensure the safety of the workers. Now keep in mind, we'll be watching one way that these safety procedures can be followed. The procedures that your company requires may be different. In this situation, a 69 kV circuit must be de-energized so that the insulators can be replaced on several poles. The dispatcher coordinates the switching and tagging for this job. To de-energize the circuit, he operates a control switch that in turn operates the appropriate circuit breaker. This opens the circuit. Then he tags out the breaker. To isolate the circuit, a disconnect switch is opened, and it's tagged out. Once the circuit is opened, isolated, and tagged out, the dispatcher is notified so he can report the status of the circuit to the field crew. The work orders given to the field crew contain information listing the job requirements and information that can help identify the correct job site, such as street names, pole numbers, or specific electrical equipment at the site. For this particular part of the job, they must replace the insulators on pole number 9994. The number on this pole does not match the number on the work order. By referring to a circuit diagram, the correct location of the pole is identified. When the pole is located in the field, the crew leader checks the components at the job site, while his partner marks off the work area. The crew leader radios the dispatcher to get the go-ahead to proceed with the job.
I'd like to install my tag and grounds on 69069, pole last 4, 9994.
The dispatcher gives the crew clearance to test for dead and install protective grounds. Although the dispatcher relays the status of the circuit, the line crew still assumes the circuit is energized until the lines are tested. The worker who will be testing and grounding wears protective equipment. On this job, the tester used is a noisy tester. The circuit to be tested is within the operating range of the noisy tester. The tester is checked by pressing the test button. The battery is okay. Now the tester is checked against a live power source. The tester works. The noisy tester is raised up to the lines to determine whether or not the circuit is dead. The tester makes no noise on this line, or this one, or this one. When the tester is rechecked, you can then assume your results are accurate and the circuit is dead. Using temporary grounds helps protect the worker in case the lines should suddenly become energized. This grounding set has 3 jumper cables. Each cable has a pole-mounted clamp on one end and a single clamp on the other. To ground this circuit, all 3 lines must be connected by the cables to an established ground. The first jumper cable connects the established ground with the bottom line. The second jumper cable connects the bottom line with the middle line. And the third jumper cable connects the middle line with the top line. The jumper cables now create one electrical path to ground for all 3 lines in the circuit. When using a temporary ground on circuit lines, it's important to connect the jumper to an established ground before connecting it to a line. If you connected to one of the circuit lines first and the line became energized before you got a chance to connect the jumper to ground, you could receive a shock. For the same reason, you want to connect jumpers to the lines that are already grounded before you attach the jumpers to the other conductor lines. Once the circuit has been switched out, tagged, tested for dead, and grounded, the repair work can be done. You no longer need to worry about the lines becoming energized accidentally while you're working on them. When the job's completed, the grounds should be removed in the reverse order, the outside lines being disconnected first. The idea is to maintain a path to ground throughout the procedure. The dispatcher is then informed that the job is completed, the grounds are removed, and the circuit can be re-energized.
9994. We've completed our work, removed our grounds, tags, like to be reported clear.
If all the work is completed on the circuit, the dispatcher can close the circuit and instruct personnel in the substation to remove the tags. Throughout this program, we've looked at various safety practices that can protect you from safety hazards. Switching, tagging, testing for dead, and grounding are safety practices that should become almost second nature to you when you're performing jobs on electrical circuits. Our protective devices are built into electrical systems, but you can't always count on them. Equipment can malfunction, people can make mistakes, and the potential for accidents cannot be completely eliminated from the system. What you have to do to protect yourself is work safe. Follow your company's safety practices so that you can work in confidence, knowing that if others make mistakes, you're still protected. Shortcutting safety practices will only short-circuit your own protection, and that's a mistake you can't afford to make.